back sometimes. Maybe like a later. Okay. So we are going to study the Chapter-6. I was thinking about you should be able to review, summarize what you learned in Chapter-5. Because Chapter-5, Chapter-6, 7, and 8, it will be on the second exam. So like summarize, review frequently is also a good habit to study. Chapter-5, we have quite a few important formulas. So just when you have time and write up those common formulas, like Boyle's law, and the Charles law. Alright, so yeah.
Where are we starting the CRE on this one?
I think we'll start on the back on 51.
51?
Yeah, 51. So write your name also on the back and write like Chapter-6 and write it here, right?
Yes, actually. You don't have to do it right now.
Alright, so Chapter-5, some of those important formulas, right? And so you have, what we talk about is the two types. So those person's name. Sometimes we call them individuals. Individual law. Okay? And then the other type is ideal. Alright, so you have the Boyle's. Even though the name sometimes doesn't matter, but so Boyle's is P1, V1 equals P2 and V2. And in Boyle's law, you will keep that temperature T and N constant. You have that form. So all those formulas you study in Chapter-5 is about these 5 variables: pressure, volume, temperature, and more. If you have some of the formulas that only have 2 of those variables, that means the other 2 are constant. Right. So Charles is V and temperature, so therefore the pressure and the N are constant. And then you have the Avogadro's, which is you have the temperature and the pressure constant, but you will see how the volume change with the number of moles. Alright, so you study this chapter, you will see like how many temperature give to you, how many pressure give to you. Okay? We call them how many sets. Okay? So you have one set, use this. That means only for one gas. When you have a gas you have like gas A or gas B, and you might have 2 pressures, but we talk about those pressure or temperature for one gas. Right. So then that is the first what we talk about. You first you have to identify which law you are going to use. Are you going to use the person's name, or are you going to use this ideal? Just see how many pressure given to you for one gas, how many temperature given to you. Once you decide that, the second problem is about units. Units and units. So as I said, in both of these 2 types, no matter the person's name or idea, so the T should be always in kelvins, T in kelvins. Then on the person's name, those pressure, volume, and N, okay, in like any unit, as long as the two are the same. Okay? Not really like that's like difficult. So if you have the pressure, if you have pressure 1 is atm, then you will see the pressure 2 should be also atm. Okay? If your pressure 1 is millimeter mercury, then your pressure 2 should be also millimeter mercury. So that's about the second difficulty. So first, sometimes you might feel a little difficult to see what law you're going to use. Just see how many things given to you, and then you worry about the unit. So that's usually the common mistake. So make sure you get the right unit. If you have to change the unit, change that. Okay? Otherwise, you probably don't want to change that because otherwise you are waste some time. Okay? So then in this type, because you have R in it, and R has different numbers. R is so-called constant. Okay? So one constant you use for R is 0.08206. And this number has a unit. Okay? This number unit is ATM times L on top, and more, and then Kelvin at the bottom. So that tells us your temperature should be in Kelvin as before, but your volume, like this L, if you want to use this equation, your L must be in liters, not like in milliliters or not in gallons. In those guys, if you have gallon for like this volume 1, and you use also gallon for volume 2, that's okay. You don't have to even like try to spending time to convert. Right. So then similarly for the pressures. So the pressure must be in like ATM. If I give you the problem and give you one pressure and one temperature and one volume for one gas, you want to find out more, you think about use this equation and then make sure your pressure should be converted into ATM and your temperature should be converted into Kelvin, your volume should be in liters, not milliliters. Right? So that's about this equation. Then from this equation, we get some other equations. For example, we have that density equals pressure times capital M divided by RT, and then this capital M is the common molar mass in gram per mole. Right. So then we talk about how to find the molar mass in different problems. Okay? And obviously, if you have the density, if you know the pressure, temperature, and you can use this formula right away to find out the molar mass, vice versa. If I give you the molar mass, give you the identity of the substance, maybe hydrogen gas, maybe carbon dioxide, okay? And you find out the molar mass, and if I give you the pressure, give you the temperature, you put into this equation, you can find the density very easily. You can also find the density at some other special conditions, for example, at STP. At STP, that means the standard temperature and pressure, the so-called standard temperature is 0 degrees Celsius, and standard pressure is 1 atm. And under those kind of conditions, for every ideal gas, we have this equation: 1 mole equals 22.4 liters. So now, if under these conditions, your density even becomes simple. You just take the molar mass, the capital M, divided by 22.4. Right. So that's about how you find the densities. And you can also use that first formula to find the molar mass, if you have the density given to you directly. Otherwise, you can find the density by yourself. If I give you the mass, how many grams of the gas sample, and what is the volume, you divide and you find out the density, then you put it back into this formula, you find out the molar mass. And we'll also talk about the second way, which means if you don't want to use the formula, this formula like D equals P times M divided by RT, or somehow you forgot, and you want to find the molar mass. So to find the capital M, you just say, by the definition of the capital M, don't be confused because we only have this 24 letters, so sometimes we use the capital M for molarity, sometimes we use the capital M for the molar mass. So when you use the capital M for the molar mass, molar mass is a gram per mole. So you can also find out how many grams, and then you can also find out how many moles, then you divide, you get the molar mass. So either way, you can, if I give you the information, you can find out the density and put into that formula, otherwise you can just try to find out the mole. So if I give you like, so given grams and volume, and give you pressure and temperature, and you want to find out the molar mass. So you can take this, divide by the volume, find the density first, then you put into this equation. If you have the density, and you have the pressure, and you have the temperature, you can solve in for this molar mass. Otherwise, you can do something like this. You can just take the gram and leave the gram here. Then you use the other three information. These three information, and you can find out what is N or what is mole by use PV equals N R and T. All right. So that we talk about in chapter 5, and then we go on and talk about those gas mixtures. So we have a gas mixture, and you can repeatedly use this equation for different components. If you have that gas mixture like the air, you have nitrogen gas, oxygen gas, and then you know like once you mix all those different gases in a gas mixture, they all have the same temperature. They all have the same volume. So what the difference for those gas mixture is the N will be different for different components, then the pressure will be different. Right? So then you can substitute whatever the mole for like a gas nitrogen, N2, and you can find out what is the pressure for N2, because that pressure is the partial pressure. Or we also studied some other way to find out the partial pressures. So we studied the so-called mole fractions. So all those use something like in this ideal gas. So if you know like if I give you some information, and you can find out the so-called mole fractions. So mole fraction as if, for example, N2, nitrogen gas. And in the mixture of N2 and O2, very easy definition, right? Mole fraction, so this will equals, if you use N for mole, so that will equals N of capital N2 divided by N of capital N2, right? Then plus N of capital O2. Because each gas, you can somehow figure out what are their moles. So once you have the mole fractions, and you usually call this, you give that a letter, so you call that X. So X N2. So now once you have that, you probably remember now, so therefore you will have the partial pressure for N2, you will call that PN2, right? That equals XN2, okay, 10 times the P total. Right, so that is about the gas mixtures. Right, I think that's, you study, like, just make sure you study all those, you know, the law we studied in Chapter 5, and then as you study for the exam 1, you will study the CRE, and make sure you not only do one time, you do like many times, and every time you do the CRE, close what you did before, and starting from scratch, and then once you finish, then you check the answer. Okay? Another way to study the CRE is to study every those choice. So all the CRE I give you are multiple choice. Okay? Sometimes those choices don't make any sense. Sometimes those other choice, if the answer is A, but the answer B, C sometimes also make sense. You can see like what kind of problem will give you the answer C. Okay. Alright, so that's about a brief summary about Chapter 5. So the Chapter 6 is about thermochemistry. Okay? Thermochemistry studies the interaction of energy with chemical reactions, with chemistry. Okay? We know chemistry is the study of matter. We know from the first chapter, right? But energy plays a very important role in chemistry. Okay? You know, a lot of chemistry reactions produce energy, so we use those chemical reactions and to use for our daily life. And also, like a lot of chemical reaction under the influence of energy. Okay? If the reaction goes slow, you can make it go faster by increase energies. Okay? And so then, what is energy? And because you want to study the influence of energy on the chemical reactions. Okay? So the scientific definition of energy is anything that has the capacity to do work. Well, why we say anything? Because in our daily life, we will see like a different format or different form of energies. You feel like you have a lot of different energies. So therefore, we have to also classify those energies. So these different energies, they all can do like, you can always use them to do some work. And so later on, we'll classify those energies because you can use them, you know, do the work. Now, what is the work? The scientific work is a force acting over a distance. So if you have so if you want to lift out something, and something has like the gravitational force, and you lift it up, and you conquer, you overcome the gravitational force. Therefore, you do some work by lifting up something. So you will have that energy or used to work, and how much energy you spend into the work, depending on how many work you do. So sometimes you might lose some energy, even though you only do like some work, and you use more energy than the work you perform because you are with some energies. And but let's say if you want to calculate how much work you did, the formula for the work is one formula for the, like those mechanical work is force times distance. You don't have to worry about this formula. It just gives you the idea. Okay? And so then the energy, we will learn those law for the energy. To what kind of law governs those energies? Okay? Which means can you creating energies or can you like destroy energies? Okay? Where the energy will go, or the energy flow from high temperature to the low temperature, or from low temperature to high temperature. So we will study those different laws. And then we know the energy, as our daily experience tells us, it really can not be created or destroyed in the whole universe, but in the whole universe, the energy can change from like one object to another object, okay? Or in the same object from one format to another format. Right. So we are going to study energy principle in this chapter, and it also is association with the chemical reactions. So as you study something new, usually you will classify something you study. And then in a physical science class, you also learn what are their units and how you measure them, how you calculate them. So we first classify them, then we'll see what are their units. Then we'll learn in more details how to calculate those energy and work and how they is changed. Right. So no matter what energy you see the light energy, you see the sound energy, and basically in a science class, so all those energy can be narrowed down into two classes of energy. I think you're familiar with the two classes of energy. One is the kinetic. If I give you one, you will think about the other one. Right? Kinetic energy is the energy associated with the motion of some of those objects, any kind of motion, translational motion, rotational motion, vibrational motion. So those are all motions. So if you have those motion, and you will carry some energies. So that those kind of energy, we call them kinetic energies. For example, thermal energy is one example of one form of kinetic energy. Right, now you can see the energy due to motion. Let's say initially, we examine this picture. We have these few objects in the picture. We have a ball that is sitting still, don't have any motion, therefore no kinetic energy. The other ball is moving, so therefore the other ball has kinetic energy. Then both of them have a lot of other energies, has chemical in the balls, and has elevation, this table like relative to the ground. So they also have the potential energies. But you can see like once this ball like colliding with the other one, and so this ball as a result of collision stopped at still and not moving at all, like the other one is moving. So you see the energy transferred from one object, from one ball to another ball. And in the transfer process, and there's a lot of things happen. Some of those energy was transferred to the kinetic energy of the other ball, and some other energy of the kinetic energy of the initial ball was lost as heat, and so on. Maybe also lost some of those little bit as sound, and because you will see the collision. Right. So as I said, you have these two larger type of energies: kinetic energy and potential energy. And so then this will be the potential energy. Potential energy is energy that is stored in the object. That means even though your object is not moving, then your object still have the potential energy. And usually it's because of the composition and the position of the object. Position of the object as a ball, you can put it in the table, you can even leave it up, like put it even higher, so therefore you have different, in that mechanical potential energy. Then the composition tell you what kind of chemical, what kind of material in it. Do we have polymers? Do we have some of those minerals? That will give you different chemical energy. And chemical energy is also potential energy. Right. So we can see this is a simple example. So if I lift up the ball and relatively to the table, so then you will see the ball immediately possess that potential energy, that potential energy come from my work, pick up the ball, okay? And you can even calculate relative to the table surface how many potential energy because of the gravitational force you have in that ball. And if you let the ball go, and you will see that the potential energy really going to and gradually getting less and less relative to the table. And then at the end, so you don't have any potential energy on the table anymore, relatively speaking. And then all the potential energy at the top is converted into the kinetic energy. And so then once it's colliding with the table, all the kinetic energy is also gone. So therefore, all the potential energy initially in that picture, in that person's hand, was converted into something else. Maybe the sound, the deformation of the tables, deformation of the balls. So all those examples tell us we have this too large group of energies, and then we also know we can convert between different format of energies. We can convert from potential energy to the kinetic energy. We can convert from the kinetic energy to the kinetic energy, and also in the same time, we lost some of those kinetic energy as heat. So then you want to study those kind of conversions. So how much kinetic energy is converted into the kinetic energy, and how much is converted into the heat as loss. So you must use those so-called thermodynamic laws. There are 4 thermodynamic laws. Really useful is only 2 of them. The first law is the conservation of energy. That is the law we're going to use in this class. Second law is about spontaneity. It's about spontaneous. So in what direction when the energy flow or when the energy transfer from what to what is spontaneous. Spontaneous process, that means once you let the process go, you don't have to intervene anymore, and it will go finish by itself. So that's the second law. And then the third law just tell you what is like the condition that will give you a perfect something. That means you don't have any chaos, any random. Very similar as everyone familiar, the so-called absolutely zero temperature Kelvin. And then briefly for the other law, we have 4 laws. The other law called the Zeus law. Zeus law will tell you if you have 3 objects, and when object A, B, and C, and if you know like if A and B in thermal equilibrium, and then B and C in thermal equilibrium, then kind of common sense, then A and C will be in thermal equilibrium. So that's about law. As I said, only the important law is about the first law and second law. So we study first law in this class. You will study the second law in chemistry 1 and 2 a little bit. Actually, that's pretty much most of the things you need in most of the classes. So this conservation law is the first law. We have a different formula to representing this conservation. And you have to be very careful. Conservation of energy in what boundary, in what limit. This law referring to a very huge something, which means the universe. In the whole universe, and energy, in some sense, if you consider about Einstein, then you will also mess you up. But let's just make it simple. Because Einstein tells you energy and matter, mass can convert. So you have to include, in that sense, you have to include mass. But in the usual sense, you will say, in the whole universe, energy cannot be created or destroyed. Or in other words, the energy change of the whole universe is always 0. But also remember, like another thing that we noticed in the last few slides, energy can easily change. You can easily change. You can change the kinetic to the potential, potential to the kinetic, or even like heat to light, light to sound, and so on. Okay? And then, even though you have those exchange, you still want to follow this principle. Okay? So that means the whole universe can sure have like no change of energy. So then in practice, okay, and we'll see in details how we use that the first law and how to study those exchange. Okay? So this just briefly tell you some of those common format of energies. For example, electrical energy. You wonder what is electrical energy? Well, it's kind of those kinetic energy that's associated with the flow of electrical charge. Most of the time is electron in the wires, but sometimes, like batteries, maybe the flow of lithium ion. You have those cell phone and laptop. You use those lithium battery, which is the newest form of battery. Lithium is very good metal. It's very light, and so therefore it's very energy efficiency. So you get better and better. You charge your iPad, you can last it for like 10 hours, and it's very very small. And heat. So this heat, thermal energy, there will be another type of kinetic energy that is associated with the molecular motion or atomic motion, because you might have atoms in your matter. Light or radiant energy, those are the potential energy associated with energy transition in an atom. So you are studying Chapter 7, you can calculate when the electron, for example, there are some other things in the matter can produce light. And when the electron transition between different states, different places, in the molecules, so it possibly can produce light, visible light or invisible light. So we all call them light. And then in Chapter 19, you will study those nuclear chemistry. So some of those atoms, nuclear not stable, they were automatically split, or human beings were trigger them, make them split, and then you will see those nuclear power plants and nuclear weapons. So those are the energy that, the so-called potential energy that was stored, associated with those particles in the atom. Right. So I can probably confuse it also these two, like radiant energy, nuclear energy. So sometimes that is similar, because if you have nuclear energy will radiate out, and so that's similar. And the common chemical energies, those are the also the potential energy that has something to do with like the attachment or chemical bond and the structure of those atoms in the molecules. And very common, like everyone uses every day, is you drive the car, you have to use gasoline. And in gasoline, and those are those organic compound and hydrocarbons most of the time. And you have the carbon and hydrogen bond, and you can convert those into H to oxygen bond and carbon to oxygen bond. So in that process, you will use those potential energy that initially in the chemicals, right? So we are going to talk about those in details, like how we use like the conservation of energy in different parts of the universe, and see which part of the universe receive energy, receive what kind of energy, which part of the universe will lose energy, lose what kind of energy, and lose how much. And all those actually very simple will depend on the first law of thermodynamics, and also depend on our concepts. And when you do those like calculation or doing those studies, you are going to use those units. Okay? So in this chapter, energy, work, and heat, you all use the same units, because all are related, and you can convert from heat to work, from energy to heat, and so on. So then when one way to see what kind of unit we can get for those energy, heat, or work is study one form of them. As the kinetic energy has the formula KE equals 1/2 times m times v squared. Now we know m is mass, v is velocity or speed. Right? And then you talk about those SI units. Remember in chapter 1 we talk about those SI units. So in SI unit system, we have some of the physical quantities. We have like 7 of those basic quantities. We specify mass, length, and time. Alright. So therefore, we just use those units. And let's see what is the basic units in the SI for the energy. We just substitute those basic units for the m, which is the mass, in basic unit. The basic unit in SI in mass is not gram, not pound, not ounces, as you remember is a kilogram, right? And then you know velocity that v means the distance change divided by the time it takes, right? So this v, so v equals d divided by t, right? And then you know d, what is d? D is the distance. Distance pretty much is length, right? Right? So this d is length, and this t is time. And then both of these two quantities are those so-called basic or fundamental quantities in SI. Remember there are 7 basic quantities. Okay? So in SI, those basic quantities, that's very bad writing. Basic, which means we have 7 basic quantities: length, mass, temperature, and mole, and light intensity, and electrical current. So those of you only usually use like 5 of them in the chemistry class. So length is 1. So you know like velocity that v, the little v means distance you travel, how much you travel and how much time you take. And so then distance is length. Length in SI is what? The little m. Well, that can probably confuse you. That this is little m, and I here is little m. And well, that's what everyone uses. The book uses that. So you have to get used to it. As I said, you only have that much letters. So sometimes the little m will stand for different things. Right? So in that formula, when we write that means that little m is mass. Right? Now here in this formula, that means meter. Okay? Right? So you substitute the unit for mass is a kilogram. Right? You substitute the unit for d, which is little m, not meter. Right? You substitute the unit for time is s, second. Right? So once you have this m over s, in the formula you have that squared. So therefore, you have to square the little m. And I said before, this little m right now means meter, not a mass anymore. There is a mass. Right? Now this little s means second. Okay? So therefore, altogether you have this unit for the energy, which is kind of very tedious, lengthy. Okay? So what do? You just give something like those special name. Okay? So you call everything together. This guy has this kind of those tedious kilogram times meter square, and divided by second square. You call that a joule. So every 1 joule, whenever you write it capital J, okay, that means you are write kg square times meter square divided by second square. Right. So that's about the units of 1 unit about energy, work, and heat. So that's only one example that give you this unit. Okay? As you know, you have a different format of energy, different format of work. Okay? If you choose to get the unit for all those energy work from the formula or the definition of KE, you get this. And if our study is right, and you will get the same unit from the potential energy. You will get the same unit from work. Right? So now I briefly tell you from work. Okay? And then I say, what is work? In physics class, work equals W. Okay? W equals F times D. Okay? So let's see how you get work. W equals F times D. So then when F in physics, F means M times A, right? Mass times acceleration is force, and then times D. Right? So now you use those guys, and you will get the same unit for your work or energy. Okay? Work, energy, and the heat, energy. Okay? So these those different things, they can convert. So they will have the same energy, same unit. You already see the unit from the KE. That is the kilogram times meter squared divided by second squared. Okay? You will get the same one from this work. Okay? See this little m. This little m is right now means mass. Right? So SI is kg. So this A means what? Acceleration. Acceleration means the change of speed. Right? What is speed? Speed is v over speed. That's v. Speed is meter over second. Right? Speed is meter over second. Then change of speed, okay, which means this guy, okay, so this guy over time, over second. Right, so to make the story a little easier, so now we have this m, which means meter. So here I will say this is the meter, okay, and then divide by second squared. Okay. So meter divided by second squared is the unit for A, or the acceleration. Right, so then the D is still length. Right? So in the SI unit, the unit for D is what? For length is what? Is meter. So therefore you have another little m. Right, so then you collecting everything together, as you can, you will have the kg, okay, times m is m squared, and then s squared, which is exactly what you get from the formula of KE. What do you call this? That guy, okay, because he studied, what he find out is this unit with that calorie. So that's another special calorie. Calorie is another unit for the energy and heat. Right? So Joule is one who invented one instrument. Okay? And he studied how you convert, okay, those work into those heat. Initially this calorie, okay, is that unit come into the world, come into is because of the people study with heat. So they find out for water, for 1 gram of water, so I think my slide will have that. For 1 gram of water at 14.5 degrees Celsius, okay, and if you increase that 1 gram of water from 14.5 degrees Celsius to like 15.5 degrees Celsius, that means you change 1 degree Celsius, that much of heat required It's equal to 1 small calorie. Then you is this guy who studied, okay, then how much work do you need? Okay? You can supply heat. You can take the water like on the stove, and you just take that out. You see how much heat you supply. You is the one who invented the instrument. You know, you instead of use those heat from like the chemical reaction or from the stove, he invented some of those instruments. So he converted those potential energy, okay, into the heat, and then that's why you find out that that equation. Right. So see that this calorie, see this one slide. See this tell you like the calorie was initially that introduced because we started with heat transfer, right? And we want to warm up the like 1 gram water. Okay? Precisely, the water will absorb heat or release heat. If you have cold water, you want to change into hot water, you will absorb some of the heat. And vice versa, you have some hot waters, rather cool, you release heat. So how much heat it will release depends on how much water you have. Okay? And obviously, precisely also depend on what is your temperature for the water. Okay? For our side, most of the time we'll forget about that. We just say that only depend on how much water we have. And also depend on what you have. We talk about water. If you talk about rock for 1 gram of rock, you will have different heat. Okay? So now you have 1 gram water, you see like how much heat it will absorb, depend on like at what temperature. So specifically initially defined from 14.5 to 15.5. So that is one Celsius difference. Okay? That amount of energy is called 1 small calorie. 1 gram water. Right. So then once you have this jet, and once you have this little CAL, that abbreviation means calorie, okay? And then we have all those prefixes what we studied in chapter 1. Right? So we have that kilo, and we have that mega. You can use all those prefixes. Right? And you will see you can have kJ. You can have K calorie. I think we made a mistake before. This K is probably a small K, not a capital K. Right? But anyhow, you have those prefixes, and you can use all those prefixes on all the units. Right? And so therefore, you can have kilocalorie, and that means you will see that is how much heat it will require to increase 1,000 grams of water by 1 degree Celsius. And we call that kilocalorie or the food calorie. Right. So this is a summary of this few common units. It's apparent these 2 common units, calorie and joule. Obviously, you can use proportion. If you increase this by 1,000 times, you increase also this by 1,000 times, right? So this is the equation. If I multiply this by 1,000 on the left side, so on this left side, so I multiply by 1,000. On the right side, I multiply by 1,000. Now before I multiply, obviously we still have this equation. 1 small calorie, 4.184 just too many joule, which we call that exact. Okay, so these are few of those conversions between different system units that is exact. Another that is exact is 1 inch, 2.54 centimeters. Not too many of those conversions between different systems are exact. But this is another example. So you either remember that or not, but you just see you have this 1 unit for the energy, the other unit for the other energy, If you multiply this by 1,000, and then you call that, well, that will be, this 1,000 means the prefix kilo. So therefore, you simply take this K with this little, little CL, then that will become, so this guy will become K CL, and K CL is the same as capital CEL. Right? And then similar here. So we know these two means the kilo. Kilo have that simple little k. And so I know you have joule. So therefore you will have that, you will have the, so if I multiply this by 1,000, so, okay. Obviously this is true here, right? So I think I will have this 4.184 kj. So now we have two equations. You can use either one. Right? So if I have this food calorie or the capital calorie, and then you know that we equals 1,000 small calorie. Understand? You don't understand, I don't understand, I don't understand. So then you have that equals 4.184 kj. Where does the kj come from? The kj come from, we keep this number, so this number, and then we will change this j into kj by combine this j with this 1,000. On the left side, I combine this 1,000 with that little CL. So little CL with 1,000 is KCL. KCL is the capital CL, which is for the food calorie. Right, so don't worry about that too much. I think whether how you convert, just remember those fundamental steps, right? So what is important is the prefix kilo, right? And if I erase all those, so you know you have like the kilo. Right? Kilo equals 1,000. And then this guy. So those what you know before. Now you just so you know like those fundamental information, and you know how to convert, how to use that. Right. Any questions so far? Not really confusing. Usually this chapter at the beginning, you will feel those all those like kind of abstract. Not too many numbers, a lot of concepts. Okay? Good. So you still like feel not too bad, right? So that's right. So now we are going to talk about how we convert between different format of entities. How we convert from heat to like energy, work to energy. We're also going to talk about converting between what and what. Now those conversions also depend on how much you have. It's very like personalized. It's like when you're treating like, or you go to like a shopping, go to a market, so you exchange your energy with work, and you have to see how much something you have. Okay? So right now we will just see. So we don't worry about exactly those numbers. Do you have like 1,000 grams of water or 2,000 grams of water? So whatever you have, if you want to study those, if you want to study this bottle of water, and you just call that is something. So what you call this word system. So whatever you are interested in to study, you might be interested in to study like what we did before in the lab. We take like one piece of those food, popcorn and peanuts, and then those is our so-called like one part of our system. right? So in the chemical reaction, I call that one part because you can call that a system, but once you have the chemical reaction, not only your popcorn, because you use the popcorn do like the combustion, so you have to take some of those some part of the air. Okay? So the one you take from the air is O2, right? So then how much gram of O2 you take, plus how much gram of that popcorn you burn, and all together you can think about that, and that becomes kind of abstract, right? So where do those come from? You think about, okay, so I have that popcorn, and I have some of those O2 in the air, so then if they come together, or they don't come together, but I just thinking both of them together make up my system. Understand? So your system is something you want to study. Okay? Maybe like, let's make it simpler, like maybe just use water. We also study those, in the lab we see that what is the temperature change of the water. Right? So once you think about, once you have a clear decision, you decide, so this will be my system. Now your system later on might lost, might disappear. Okay? That depends on what kind of system you have. Okay? Your system can change, or can exchange, can interchange, okay, with something else. It can interchange the energy. It can also interchange the mass. So therefore you only have that in your mind. You probably don't really have that physical boundary. Okay? You think about I will use a bucket, say that's my system, and that will never change. Okay? So have an open mind. Okay? So depend on what system you have. Right. Now we also learned that the first law. First law is about universe. Universe, our world, our sun, and our moon, and then Jupiter, Mars, and Mercury, and all those our solar system, and our Milky Way galaxies, and some other galaxies. So all those together are universe. Okay? Right? Now that's first law. So therefore, the first law is a very precise definition. Okay? So in the whole universe, so energy can never change. I mean, you have that total amount of energy, you are never lost and never gain. Now to study that a little easier, so we will just divide. Okay? So we will divide the whole universe into two parts. One part is something you want to study. You might want only study those water in this bottle. Okay? And then you will see everything else. Everything else is other part. Divide into two parts. And our system and our surrounding. Everything else is surrounding. So then this first law just tell you, okay? And the energy change of the system plus the energy change of the surrounding equals 0. Okay? So if I use delta E representing energy change, so this is an energy change. This is for everything. Okay? Energy change, and you know this E that makes sense with energy. Okay? Now this is delta, this capital delta always means change. Okay? Alright, so energy change. Okay? Now we just keep like be more precise. Okay? Just use those subscripts to tell me the delta E of what. Okay? So if I set delta E universe, so therefore is the energy change of the whole universe. So then according to our first law of thermodynamics, we know this is how much? This equals what? Equal to 0. Okay? So the energy change of the universe equal to 0. Right? Now those energy, okay, is additive. The energy change is also additive. So you have the two parts in the universe. You have that system in one part, and surrounding another part. Right? So each part has this delta E. So this guy has a delta E, and this guy will have a delta E. So again, you want to be more precise, you give them some name. Right? You will call this delta E. If I use abbreviation, I just call that delta E SYS, which means system. And this one I will just call that SURR, which means surrounding. Right? So now you know, like the whole universe energy change is the delta E universe. Right? Right? So now you know the energy change is additive. You can also use abbreviation delta E universe. That will equals delta E SYS plus delta E SURR. Right? And this again should equals what? Should equals what, man? Equals 0. You can write like that, and in your mind you know this. If this part, you just take this part into consideration, this will change into something that is used as sometimes a loss. Delta E SYS equals negative delta E SURR. Right? Yeah. So that means the energy change of the surrounding and the energy change of the system, they have the same magnitude but a different sign. The sign will tell you either you lost or gain. Okay? So that's what it means. Okay? I mean, when the system, for example, lost energy, and then all those lost energy is received or gained by the surroundings. Right? So then, depending on the problem, what kind of experiment or what kind of problem is easy to measure what. Right? If you want to study how much energy change for the system, you can measure the system directly. Right? So if you think that this bottle of water is your system, right? You are observing this bottle of water. This bottle of water, the temperature increases or decreases, or do some chemical reaction. Then you want to see how much energy it received or lost. You can sometimes measure that directly, right? Otherwise, if you cannot measure that directly, for example, like what we did in the lab, we want to study how much energy those popcorn has, how much energy those peanuts has, right? And obviously, we cannot really measure the temperature of those peanuts and then the temperature of the before the combustion, after combustion, so that it's easy. You probably can also invent some way, but when we just measure not easy to measure something else, okay? Then use this equation convert. Okay? So therefore, we study those energy change between different objects. Okay? Is that useful? Now this definition is kind of very not very sharp, because what we said is this is our system, for example, bottle of water. Okay? Everything else is surrounding. The bottle is surrounding. Okay? The table is surrounding. Okay? The air is surrounding. Then depending on room temperature, so those all surrounding variables. Okay? Right. So then you want to use either one to study. So better probably not only isolate or identify your system. You also want to isolate, identify what is your surrounding. So once you like identify your surrounding, then you can either like measure precisely or calculate precisely what happened to the surrounding. Then use what happened to the surrounding, reverse the sign, and put that to what happened to the system, and vice versa. Right. So right now, as I said, we still like just concerned about the everything together as a system. Right? We just say this water bottle as a system lost how much energy. Right? And then later on, we will become like more precise. We'll say if this water is pure water, then we can like study, define, and how many like every 1 mole of water or every 1 gram of water. Lost how much energy, gain how much energy. So once we have that, we can just make those into like some of those table data, and then like if you are the one that first studied, then people later on can use what you studied. So we define surrounding as everything else, but this everything else, obviously everything else in the universe. And so you sometimes you will control that, confine that into like all some of those limits, then make our study like very easy. But as you saw before, like what we talk about is. We have this equation. This equation is one format. So this is one form of the first law of thermodynamics. So later on, we will get another form of the first law. Right, so then, as you knew before, like in some other chapters, so we talked about the change before. Any change, no matter it's the change for the energy, or the change for the temperature and pressures, always have this sequence. It's always the final minus the initial. So whatever change you talk about, if you talk about the change for the pressure, and you want to see how much pressure change, you will find out what is your final pressure, what is your initial pressure. You take the final pressure, subtracted by the initial pressure, you see how much pressure change. Similar, if you want to see how much temperature change, so if I want to see how much temperature change, I will just call that delta T. And later on, you can be more precise. Delta T for what? Delta T for water, delta T for the air, or delta T for the surrounding. Right? You can call either one your system. Right? So you can call that system. Right? So right now, let's omitting those. Right? Just emphasize these very basic concepts. So the change is always the final. If I call that Tf is our final temperature, and if I call our Ti our initial temperature, then you take the Tf minus Ti, you get the delta T. And if this Tf is for our surrounding, and this Ti is also our surrounding, then you get the temperature change for the surrounding. If this Tf is for your system, and this Ti is your system, and then you will get the temperature change for your system. Right? So all the other quantities will be similar defined. Right? I think that is very straightforward. So once you have this, and in this picture you will see you have one part clearly your system, the other part is clearly your surroundings, but as I told you before, usually in reality, you don't have such a clear boundary. Okay? So your border between these two guys, between the cysteine and your surrounding, usually not that clear. And sometimes you don't even have a really a physical boundary, because you can interchange the energy between these two. You can interchange the work between these two. You can also interchange the mass between these two. But conceptually, so we have these two parts for our universe. Okay? Now, once you have these two parts, then you know each part has their energy. Okay? So therefore, each part will have the energy change. Okay? So you can see if I use those arrows to representing those decreases or increases, okay? And then you can see these two parts will happen opposite directions. So if one decreases, the other one will increases in terms of energy. Okay? And obviously, they will have the same magnitude if you put them in the same unit. Right, any questions? Right, now we talk about this energy, okay, it's kind of, is what we said, okay, is the internal energy, okay. So the internal energy, okay, and for our cysteine or our surrounding. Okay? So when we talk about one, just think about one. Okay? And then you are thinking about how they interchange between the two. Right? Right? So the internal energy is the total amount of all the energy, because we know all the energy is these two smaller groupers, either kinetic energy or the potential energy. Right. So this slide will tell you, you have this two part of the universe, and if you, sometimes your system is huge, and sometimes your surroundings are also huge. So both of them are huge. But usually you need to like make them easy to study. So you see like this is the part of the universe. This is what I want to study. This is for the cysteine. Now I can also, depending on what I study, I can also isolate, or isolate the other part from the universe called the surroundings. Okay? All right. So then this internal energy is for this first definition. This first paragraph is for each one. Okay? If you think about it for the cysteine, you just keep thinking about it for the cysteine. Okay? If you think about it for the surroundings, you think about it for the surroundings. I think here we're thinking about, for most of the time, we think about the cysteine. But those two you can interchange. Right? Right? So now let's concentrate on what happened to this part. We call that cysteine. Right? Right? So what is said here is the change in the internal energy of the cysteine. And that is also true for the surrounding. If you keep thinking about surroundings, okay? Let's think about for the cysteine. Okay? So the change in the internal energy of the cysteine only depends on the amount of the energy in the cysteine at the beginning and at the end. At the beginning we call that initial. At the end we call that final. So those kind of quantity, like here the quantity we talk about is the internal energy. So this internal energy, because it has this characteristic in this second paragraph, which means the change, the internal energy for the cysteine the change of the internal energy for the cysteine only depend on the beginning and end. It will does not depend on how you make the change. So those kind of quantity, we give them a special name. We call them a state function. So this is state. So this state is not our, not only the solid state what we talked about before in Chapter 1, Chapter 2. Remember we said in Chapter 1, Chapter 2, we have four states, three common states for matters, solid, gas, and liquid. So those states here, not only that, including those information in it. Right? So this is those kind of quantity, those kind of physical quantity that whose change only depend on the state, only depend on the beginning state and end state. We call them a state function. And so then that is one way to think about the so-called state function, whose change. If you don't like to think about the change, just think about its value, whose value, the value of the internal energy, the value of your pressure for like the value of the pressure or the temperature of water. Temperature of water, those are also state functions. So those only depend on the state. So as I said before, this state, not only the solid state, liquid state, there are other information, more information. So you have to specify what is the temperature, what is the pressure, what is the composition, those altogether specify the state. Right. So therefore, thinking there is another way to think about what is a state function. A state function whose value only depend on the state, that we call that state function. And those states we also call them condition. It will not depend on how you get to the conditions. Condition of this bottle water. So right now room temperature, atmospheric pressure, pure water, and this elevation. So therefore you have this much energy in it. It has the kinetic energy, it has the potential energy. So it does not depend on how you get this water. This water can come from you melt the ice. Or it can come from you cool some of those hot waters. So no matter what you get those waters into these conditions. Right? So now let's continue with our change of the energies. Let's see, we are interested in studying some of those chemical reactions. Right? So as I said before, so you have that argon plus oxygen gas. So that's your cysteine, right? So your cysteine, and so then this is our reactant. So our reactant is kind of our beginning, our initial state, right? So then this will go through those combustion reactions, right? And it might produce H2O. That is the only produce H2O, but this is the common, right? And then produce carbon dioxide. And these two are our products. And then you can here be more precise. So what is our initial? What is our final? You can very like just very like broadly say our initial state is that our initial state. Our final state is our final state. More precisely, you will say our initial state for our system, which is that much of power current plus that much of oxygen gas, is our power current and oxygen gas before the chemical reaction. Right? So now after we make them to go through the chemical reaction, we produce those products. We see what we produce is H2O and CO2. And this, we give them a little more precise definition. So these two are our so-called products. So and the product, that is our final state. And then you will say, now what is our energy change for our system? So I say, you will just take those common notations. So E is for energy. So energy of the products minus energy for the reaction, and we call that delta E reaction. Now that reaction you can give like you can call that reaction, or you can call that system. Okay, that's my system. So in a broader sense, you call that system, right? Then in reality, in some of those specific problems, your system might become simply like water. So water becomes your system. Right? Or your chemical reaction becomes your system. So don't be confused by that. So you will see that you have some, a lot of times you have a different name. You sometimes you don't use that very broad like a system or surrounding. You give them like a little more specific name. But in your mind, you still have that two parts of universe. Right? So one part is your system, the other part is your surrounding. Right? So the internal energy is a state function. It only depends on the initial state and the final state. And so then how much work something did, how much heat something produced. So that two quantities depend on the process. So therefore they are not state function. Right? So let's see, we have this system. So our battery, let's see, this battery is what you want to study. The battery becomes your system. Because you can choose anything as your system. So our battery is our system, right? So therefore our battery has the internal energy. So you have the internal energy for the charged battery, and the internal energy for the discharged battery, right? So even though you don't know, usually you are difficult to calculate absolutely how much kilojoule or how much like a kilocalorie of this battery has the so-called internal energy. But you can measure and calculate how much it changed, how much it lost from one condition to another condition. Right? So one condition we call that a charged. And another condition we call that discharged. You can call them either an initial or final, depending on what you study. So if you want to study the discharge process, right? So how much energy the battery, charged battery will give to you, right? And you will call this charged battery your initial condition, and the discharged battery your final condition. So then as I said before, even though you don't know or you cannot measure or calculate absolutely how much energy, how much internal energy this charged battery has, but you can calculate how much it changed. Okay? So how you calculate how much it changed? Okay? Well, you can do either like measure like those. If you can measure, well, so you cannot measure like or calculate exactly how much in the battery, but you can see what it do to something else. We call them surrounding. Okay? So you mix up those devices, okay? And you have this charged battery, you discharge it, you can you can like drive like a fan. And then when you drive the fan, obviously the fan like will tell you what is your like power, right? Therefore you can calculate and how long the fan run, and you can calculate how much energy the fan used. And then you probably can measure how much temperature change for the fan. And then this pretty much the two common way that we interchange the energy between the silicon and then everything else. Everything else, besides the battery, is the fan, the wire, the air, and so on. Right? So you can probably cannot measure, calculate, what is the energy change derived from battery, but you can calculate how much work this battery did on the fan and how much heat it produced. Okay? So by that, you add them together, and then you switch the sign, and then you will see how much energy change for the battery. And then, no matter what you do, so we say this internal energy of the battery of something in the silicon is the state function. So this change from this level called the initial to this level called the final. So this gap, you know that for sure. Right? So you call that gap is your delta E silicon. Right? And adding together this gap, and you can either you don't use this energy to anything useful for work at all. You just lost all the energy of this charged battery as heat. Or you can use that do some work, and so therefore you have most of that you use that to do work, but you still lost some of it as heat. Right? So in this 2D example of two process, okay, and we have a different amount of heat. Here's more heat, there's less heat for the same battery, okay, and there's no work, more work for the same battery. So how much heat we use or we get from the battery, how much work we get from the battery, depending on the process we use the battery. Those kind of quantity, okay, is not a state function because it depends on what route, what process you use. Okay. And then in compare, the energy, the internal energy change for the battery is this gap. So no matter what you use that doing some work or doing no work, and the energy change for the internal energy change for the battery is just this much. The gap between the top line and the bottom line. Alright, so that gives us some good comparison, good example of the state function, state function and non-state function. So the function, you can just say your function is either a state function or non-state function. Okay? Depend on the value for the function, okay? Only depend on the state or not. Or it depend on the change of those functions. Whether it depends only on the initial or the final. If only depend on the initial and the final, does not depend on the process, then we call those kind of function, a state function. Function, that's just another name for those physical quantities. Mathematical function like y equals cosine x. I mean, when you have an x, you will get some y for that, right? So that's similar for those physical quantities. So whenever you have those conditions, you will have a number for those quantities. Okay? So if that number only depends on the state, then you will have the state function. Right? You compare some of those quantities like in your life, for example, the altitude or the elevation. elevation and compare with like those path lengths. This altitude is same as elevation, right? So altitude, you know, how much change of your altitude when you climb a mountain. And that does not depend on which path you use. Okay? Whether you use an easy path, so that probably will take a long travel, or you take a difficult path that take like less travel but it's difficult to climb. And the altitude, the change of the altitude only depend on your, if you want to climb all the way to the top and the base. Right. So then you can also represent, those energies, for example, those internal energies of the system, of the surrounding. So again, I will show here system, all the other parts, surroundings, as an energy diagram. An energy diagram is a very useful way to understand something. Okay? So you study more and more science class. Okay? So usually you will try to use an energy diagram to understand something. Okay? So you will draw like the one axis, okay, usually the y-axis is energy, the other axis is something else. But in this energy diagram, we don't even like have this axis here. We don't have that, but we just use those you know, the initial and the final state. Alright, so then this energy diagram gives you a relatively visualized way to understand whether your internal energy increases or decreases. That is very, very straightforward speaking. Right? I think that's also like useful because you can see the internal energy increases. That means your final is higher than initial. And then from those kind of diagram, we get an impression. So we call that delta E. Delta E is our internal energy change. Is a plus. So when you have a plus, that means your final is higher than the initial. So that means your quantity increases. And I think about the other possibility. And the other possibility is you have this energy diagram, you still have this energy axis here going from bottom to the top, increases. But depend on your process direction. Your process direction depends on where is your initial, where is your final. In that one, your initial is lower, your final is higher. So therefore, your energy increases and you have this delta E plus. And here you just do the reverse. So your initial is higher, your final is lower. And if you do a subtraction, obviously, this number here is smaller, which is a small number. In subtracting by a large number, you get a negative number, which means, so you lost some of those energies, right? So now let's think about the interchange between these two parts of the universe, right? So again, I draw here kind of just a diagram to illustrate these two parts of the universe. So we have this system with the blue bar, and then this yellow square beside the blue bar is for the surrounding. You might not have such an idea or situation, so we probably don't have those boundaries here, and usually we don't have, not so easy to isolate this part as our surrounding either. But to some approximation, we see that is true. So now we can see these two diagrams. This diagram shows, this, we have another diagram here. So this diagram here, that you can see this delta E is negative. That means your internal energy for the system decreases. You go from the your initial is higher, your final is lower. So that all those energy lost from one part of the universe might get into the second part of the universe, might get into the second part, and third part, and fourth part getting into many, many parts of the universe. But what you can do, you can see this part is my system, but everything else, part 1, part 2, part 3, the table, I think this what is our system. The bottom is part of the second part, right? The table is another part. And when the energy, when something happens to the water, so either the temperature increases or decreases, and then those energy associated with this water change will come from the plastic bottle, come from the table, come from the air, come from everything. So you can just think everything else just adding together in your second part, in your surrounding. Right? It's very easy, very straightforward. So if your system decreases in energy, then your surrounding will increases in energy. And I have this equation here to tell you, again, that's what you saw before. So vice versa, if the surrounding lost internal energy, okay, that means those internal energy come out from the surrounding, getting into the system. Now you know as a result, your delta E for the system should be positive because that's the change means positive means increases. And then you have this equation. But this equation still has what you saw before. So if you move these two, if you change these two equations, you move this to this side, that means this one plus that one equal to 0. That's just the one way to see the conservation of energy of the universe. And similarly here, right? So if you plus 1 here, so this one cancels with this, and you plus 1 on the other side, so therefore, in adding together the energy change for the system plus energy change for the surrounding equals 0. So no matter where you put the negative sign, it'll tell you the energy change for the system and the energy change for the surrounding just opposite in sign and same magnitude. Right? So theoretically, ideally that is true. Right? In the experiment, we measure that, how good this is true depends on our technique. Right. So once we understand, we have this interchange between the system and the surrounding. Okay, so we have this general equation is delta E, right? System equals negative delta E. Forget delta. Surrounding, right? So this is always true. This is always true. Right. So then, another way to see this equation is to see how much energy your system gain or loss, right? And then that will equals this change, right? So instead of writing that equation, you can write your delta E system equals how much heat your system gain or loss, and how much work your system gain or perform. So that is the only two ways that you can like interchange energy between your system and surroundings. So I can either emphasize this delta E system, it will equals the negative part of the delta E surroundings, or I can just emphasize how much heat this system loss or gain, how much work this system perform or receive, and that's adding together so equals how much energy, internal energy change of my cysteine. Right? So this gives us a variety way to measure or calculate the delta E, or the internal energy change of our cysteine. Right, so this is another equation. So this equation is our second form of our first law of thermodynamics. You still remember the first form, right? The first form is delta E cysteine equals negative delta E surrounding. So this is our first form. So either way, depending on what you emphasize the interchange between the two parts, and you use the first one. And you know, if you know some way, you can calculate how much heat that's the first. How much heat, which we use Q. How much work we use W. For your cysteine or for your surrounding, depending on what is easy to measure. So in reality, so this what I write here for either one, for either my cysteine or the surrounding. Understand? So now let's think about this in in the viewpoint of cysteine. In the viewpoint of cysteine. And you can change this in the viewpoint of surrounding. So then I'm going to use this equation to calculate. So assuming we have some way to calculate how much heat released or gained by the cysteine. If you want to do that for surrounding, use the same idea, same definition. And how much work the cysteine perform or received from the surrounding, we call that W. Right? So this is one definition. If you study the same times the general physics, that might confuse you, because general physics has different definitions. Alright, so let's just identify in this table. I just want to make sure everyone understand in what process. Or give you the number for the heat, give you the number for the work, and you just decide what sign it has. It's easy, either plus or negative. It's also easy. Everything make that the internal energy increases is a plus. Right? Anything make the internal energy, anything make this E, make this E increases is a plus. Anything make the energy decreases is negative. Right? So what about when the cysteine gain heat? You see, we talk about this delta E is for cysteine. So all those is for cysteine. All those for cysteine. Now if the cysteine gain the heat energy, will that make the internal energy increases or decreases? Increases. So anything increases, anything make the internal energy increases, you will put a plus sign. Right? So now let's see about work in another process. So if in a process, the cysteine gain energy from work, right? Means the cysteine not doing work, maybe doing less work and receive more work. So as a result, the cysteine is gain some energy from the work, right? And then that if you receive work as a net result, right, that will make the internal energy increases or decreases. Increases. Anything make the internal energy increases, the plus. Right? So now once you decide this plus or negative, then you just remember you have these equations. You have delta E equals Q plus W, right? That's easy to memorize. So that's only two ways we can change the energy between any two parts of the universe, either as heat or as work. That is a very broad definition because you can have different work. You can have electrical work and mechanical work and all different work, right? But there's these two larger categories. Right, so then if you have these two numbers, one is Q, one is W, both numbers is plus, then you know from your autograph, the plus, you will get what? Get a plus. So your delta E will be plus. Does that make sense? Okay, now what happens when the system releases heat? Release heat energy. If your system releases heat energy, what will happen to the internal energy? It will decrease. Anything because the internal energy decreases, right? It has a negative sign, right? Negative sign. Let's see what happened to the work. What about the system release energy by doing work? If you're doing more work, then you probably again you will do like you have both process. You're doing some work and you also receive some work, but as a net result, right? You're doing some work. If you're doing work as we define, what is energy? Energy is anything that has the capacity to do work. So when you do work, you need energy, right? So what is the sign for this W? Negative. Right. So now very similar situation. You have a plus, you get a plus. What happens? You have a negative. Again, you have negative, you will get right? You get a negative. No, not a multiply here, right? We don't see negative multiply a negative. If negative multiply by negative, you get a plus. Here we are adding, right? So here this is adding. So you have adding a negative and with another negative, you just get more negative. Therefore, you just have negative. Right? Especially what happens in this one, when the system gain heat, this is plus or negative. I would say plus, right? So what happens to this one? Doing work for this kind of W. Negative. No, that's can you decide like precisely or beforehand? If I just tell you just the heat is plus, the Q is plus, W is negative, what will happen to the delta E? Possible. If the magnitude of Q, right, equals magnitude of W, right? Okay, so then what else you can say? Either 0 or what?
No change.
No change. 0 means no change, right? That means if the system like perform some work and then also gain some heat. So what you receive equals what you use, so no change. What other possibility? I just tell you we have a plus Q, negative W.
It depends on which number it is.
Which number is bigger? Okay. What about if Q is bigger? I mean, just forget about the sign. Just have a lot of Q.
Positive.
Positive, right? So if I have a positive like I have a positive 10 joules, right? It's just one example, right? One example. Because if I don't have a number and I have a negative 5 joules, positive, right? So in another example, if I have a positive 10 joules, but I have like 15 joules negative. So depending on like which number is, what downside is also right. If I have a positive 10 joules and negative 10 joules, that means I gain 10 joules from heat, but I use 10 joules to do work. So therefore, your adding becomes 0. So you have all the possibilities. I think that reminds you price or change plus, negative, or 0. We just see either plus or negative. Alright, so that means this kind of Q. If the system release heat energy, negative, very good. And so what about if the system gain work from gain energy from work? Positive. So now if you have a negative and positive gain, then what is the possibility for your delta E? Positive, negative, positive or negative or zero. Right, so this is very, very important to recognize. We have possible sign either plus or negative for the heat or work. Any questions? Comments? Alright, so now let's use that equation. The one way of writing that first law is delta E equals Q plus W. Q is for heat, W is for work. So we have a very simple process and very simple example. And let's think about whether this example will follow or obey this equation or not. Okay? Or we can use those numbers to verify this equation and what we studied is true. Alright, so let's first calculate from those given information what is our delta E. We think about our in this example again we think about our delta E is for one part of the universe is our system. Our system. Okay? So what is our system? Our system is this ball. Okay? And we want to use this picture to calculate what is our delta E for this ball. Okay? You know this E is the internal energy. Right? Internal energy including all the energy. But when you calculate this delta E, you just calculate those parts that is changing. So you just calculate those energy that is changing. So now in this picture, we have a lot of energy in this guy. Right? We have the potential energy, we have the kinetic energy, we have those chemical energy in it. Right? And now you think about in this process, you starting from this, let's say this is our initial, and this is our final. Let me fit in this initial and final. Okay. So I think about this process when you go from the initial to the final. What are those energy for this system are changing? Is potential energy changing? I mean the gravitational potential energy, is that changing or not? We're assuming this table is horizontal, not kind up, not goes down. Right? So you don't change the elevation or altitude, so this ball's potential energy is not changing. Right? Is this ball's chemical energy changing? From this initial to the final, is this ball's chemical energy changing? Or not that too much, you might just a little colliding, right? And in the cleaning process, you might break a few those chemical bond or the paint or something, but probably not that much. Okay, so what is changing for this ball is only what? So this is our only changing, only our changing part. Only our changing part. Now, do we know the information for the kinetic energy of this ball of the initial and the final? What is this ball's final Well, first of all, when you have those change, delta E, okay? So we will see this will be our, we pretty much want to see those energy, okay? Minus energy, okay? Because all the other energy are not changing, so only this KE are changing, so therefore I only consider this KE here. So KE what minus KE what, when you see the changing. So the first KE shall be what? The second KE shall be what? What will be our use like final and initial? The first KE shall be KE what? What is the first KE? This KE shall be KE, the initial KE or the final KE? The final, right? So this is the final, and this is the initial. Do you agree we change our more general definition? In general, you will see this delta E. Delta E will equals EF minus EI, right? So we use a simple version. We don't use EF because E were including all those energies, potential energy, kinetic energy, and chemical energy. If you use them in that, they are not changing, they will come out, right? So therefore, you only see the changing part, right? So now let's see these two like pictures. What is our E? What is our KE final, and what is our KE initial? What is our KE final? Anyone? Zero here, right? So this is the 0, and what is our KE initial? 5, here the initial KE, right? So both of them has unit joule, so therefore you get negative 5 joule. Right, now we want to verify this equation. So right now this equation, the left side is negative 5 joules. Okay. If you want to verify this equation is true, and you shall find those information, get the number for Q, get the number for W, and you add them together, you shall also get negative 5 joules. Alright, so now let's see, do we have information for the Q? So Q equals how much? W equals how much in this process? In what process? In this process, you have this process for this system, for this ball. So this is our initial state. And I'm running, colliding with that one. In the running process, lost some energy and the heat, then collide. And in the colliding process, what happened? So before the collision, you still have some energy, and after colliding, all the energy totally, and all the key totally gone. Right? So tell me, what is our Q for this process? What is our Q? Q is what? Q is W. Q is work or heat? Okay, so Q is heat. So we see heat in this picture. Where is the heat? 0.5 joule. Right, so I will write 0.5 joule. Now you tell me the sign. What will be the sign for this Q?
Negative.
Why is it negative?
Using it.
It's loss heat. So if our core is our system with loss of heat, which means that will not make your energy increase, make the energy decreases. Alright, so now how can we find out the work? How we find out the work? Well, the work, there's an interchange between the KE and the work, right? So what kind of work this board did? What kind of work this board did? Tell me what kind of work this board did. This board did some what work? What did it do? Now what work is this? It move this blue bar out. Okay? So now that's moving the blue bar doing the work. And doing how much work depends on what energy it has before doing the work, and then what energy it has after the work. So before doing the work, it has how much energy? Has 4.5 joule kinetic energy. See here? Kinetic energy at the collision, actually right before the collision. And the kinetic energy after the collision becomes what? Becomes 0. So therefore, that 4.5 joule of kinetic energy is totally used at what? At the work, right? Right. So you have a 4.5 joule of work is performed, is did. So if the bar did work, and that clear, make that KE disappear, right? So therefore, it makes the internal energy decreases. Now this 4.5 joule shall be what? Shall be plus or negative? Very good. So you perform work. Or what you study in this case is the bar you call this bar is your system. So then in the viewpoint of the system, if you are doing work, you will use a negative sign. Right? So then we will have these two numbers. So you put on this side, you have negative 0.5 plus a negative 4.5. That gives you altogether negative what? Negative 5.0 joules. Right? So therefore, we verify that equation is true. Right? And so this is one example. Remember in this example, and we have our delta E. So we have our delta E on that side, negative 5 joule. And we have that Q plus W is also negative 5.0 joule. But we have a different number. I mean, we have these two numbers for Q and that number for W. Okay? So what we have for here is this Q is negative 0.5, and then we have this W 4.5. Alright, and so that's about that. Now we use a similar equation and for a different process on a different table. So we still have that equation delta E equals Q plus W. Similar calculation, what will be our delta E? Delta E will equals, in general it will equals EF minus EI. In this particular process, we will call that equals KEF minus KE what? KEI, right? So we have this change from that equation to this equation. That is only true for this kind of process. In this process, we don't have any other change for the energy for these two balls. Only the kinetic energy are changing. Alright, so then what is our delta E? What are our KEF? And what are our KE emission? Again, you see all those numbers in the picture, right? So what are our KEF? What are our KEF? Zero again? What are our KEI? 5. 500. So therefore we get 500, negative 500 joule again for the delta E. Alright, so then let's also identify, so not let me first write on this part, we have negative 500 joule for this guy, right? And that's, we get that from this very straightforward definition. Now let's calculate this part. which means we have to find out what is our Q and what is our W. Right? So again, you know like what the Q is standing for. Q is for what? Q is for heat or work? Heat. W is for work. Right? Now let's see, this picture tell you how much heat you lost or gain in the process. And how much heat we lost or gain. Okay, let's see this number here, right? Heat loss. If heat loss is positive or negative? Negative. Okay? Negative 3.0 joule. Right. Now let's see the work. If this bar, so this bar is our system. Okay? So this bar doing work, or this bar receive work. It's doing work. Okay? Doing work by making the blue bar moving. Right? And how much work it did? In this process, how much work it did? How much work it did depends on how much energy they use. How do you know how much energy they use? Depends on how much energy it has before you do the work, and how much energy it has after the work. Right? So how much work it did? So initially you have 5 joules, right? But those initial 5 joules, 3 of those is lost as heat. It's only 2, so before the collision there's only 2 joules. Okay? And that is the energy that the weather rod doing the work. Right? So then you have 2 joules. Now these 2 joules is positive or negative. If you're doing work, you use what? Use energy. Right? If you use energy, that will make the energy lower. If you receive work, you don't need energy. Right? So therefore, this 2 joule is positive or negative? Alright, so negative. Now you have this on this side, so therefore we have this negative 3.0 plus a negative 2.0, and this gives us a what? So as I said before, and here you have 2 numbers you are adding. You have a negative 3.0, and then you adding a negative 2.0. Understand? Right. So therefore, these 2 like 2 processes representing 2 different processes, and so therefore you have a different Q and W. And Q and W are not the state function, because it depends on the process. Alright, so let's try to use what we just started to do some of those calculations. Okay, so I will read this question. And we will see we have a universe again. We have a potato cannon, and we have those. Obviously, we have those metal parts, and we have this potato, and we have some of those fuels. Right. So in any of those processes, and you can decide and pick up one part of the universe as a system. All right. So let's see what we choose. Let's choose this one. Okay. Let's choose the fuel, right, in our system. Right? And we want to calculate this delta E system. What equation shall we use? Shall we use that? Shall we use that E cross delta E surrounding, or should I use delta E system equals Q plus W? I think we have to use the second one, right? Well, we don't have any information to calculate what is the energy change for the surroundings. Because the surroundings, as I said, if you see your system is a fuel, everything else, the potatoes, the cannon, the metal, all those areas is our surroundings. So we don't have enough information to calculate the energy change for that. But we are given those heat loss, so even though in this statement it does not tell you you call that system. Just tell you to calculate the delta E for the burning of the fuel. Just tell you to calculate the delta E for the fuel. Right? But you can give it a name. You call that a system. Alright, so then let's just identify Q equals what and W equals what. Then we'll put it back into the equation and find out the delta E. Alright, so the first part is that it performed this amount of work, which means it did some work. Did work, need energy. Okay? Need energy, that will make the energy of this fuel decreases. Right, so if you have this 855 joule, and this 855 will be a negative. Right, so then the other part tell you it produces this much of heat. Right. So therefore we know this Q equals 1,422 joules. Right, now 1,422 joules, that is the heat. Okay. Now this heat is release or gain. Release or produce the same, right? In some sense, produce means or not release right away, but release. That makes sense? So therefore this will also what? Negative. Alright, so again you have these two numbers. First you have the same units, now you can add. Okay? So both of them is joule. Joule is unit, joule is a unit. I think that makes sense. When you're adding something or subtracting something, make sure they have the same unit. Right, so I'll just substitute those numbers. We have like 1422 plus 855, and both of them, so this is joule, this is joule. Right, so just adding them together, you will get what? 7, 7, 2, and 2. Am I right? Yeah, I think that's right, right? Right, so this is one example of how to do the calculation for the energy, like in this chapter. Right, so now you do a similar practice. Right, so you start on the scantron number 51. Is that right? Yeah. So what equation should we use? I think in these few chapters, it's little easier than the first few chapters, where you pretty much just see that you memorize some of the equations. Not really, you have to find out those relations. what equation you use, and then you decide in that equation what you have, or what you need.
Is it C?
Is C? Is that C? How you get C? You use what equation? Yeah, so that's good. Delta E equals Q times W, and this is what? This is 488. Doesn't work, so that means negative. Very good. Absorb means plus, so that's plus. And both of them mean Q, right? Very good. Any questions? Did you get C? You get C? Okay, just be careful with the sign. What did you get? You got C? Okay, so for this one, because we only have, no, not that one. Alright, so later on you probably want to use that equation, like delta E, the system equals negative delta E, like surroundings, okay? Or any other part. Or for this problem, we use delta E, system equals Q plus W. So once you know this equation you want to use, just identify Q is sort of the height, and W is what? W is the work. So you see those questions will tell you like you do a different way. So you see this is a height, okay? I tell you absorb, so therefore you have plus 3590, and this is the work. Then you see the word, the key word does, the did work. So therefore the W work equals negative 488 joules. So that's so easy, right? So for right now, you just know like because you don't have information for the other part of the universe. So later on, when you have two parts of the universe, if you have the other part of information, you are going to use that equation. Right? So therefore, you have 359 joule, and then plus negative 488 joule, and that will give you negative 129. You said it's C, right? Yeah, so that's just very straightforward. Similar. And we did a very quick calculation because they have the same unit. I think that this one just as what we usually do is make sure when you adding something or subtracting something, this will have the same unit. And if you can do the last one, you can do this one. It's very similar. And just make sure you get the same unit. Well, absorb a heat, that means the heat should be plus, right? Okay. So the surrounding do work on the system. That means the system also receive work. So therefore the work is also what? Also plus. Okay. Now you have plus and plus, but make sure the unit will be the same. I think this is a little like tricky. 1 unit for the heat is what? 1 is joule, right? And the work is what? Kilojoule, okay? So you know how to convert from joule to kilojoule. Okay, so what's the answer? What's the answer? E. Right? So just know like 1 kJ equals 1,000 J. You can do either conversions. I think all those answers is kJ. So therefore, you have to convert all those into kJ. Alright, so you first identify, you want to use this delta E, and we call that a silicon. So that will equals Q plus W. So the Q, and we see is absorbed, the silicon will absorb. So therefore we have plus 3294 joule. Then we use this equation here, what we do like since the first chapter. Okay? So I hope that by now I think most of you are doing very good with those kind of conversions. Right. So Q and Q cancel out, you get 3.214 kilojoules. So we still have a plus. And so then we identify the work. Okay? So surrounding to the work, surrounding to the work is surrounding to this work on the silicon. So therefore the silicon receive work. Okay? So who doing work, be very careful. Okay? So you are calculating this number for the silicon. Okay? So the work is not the silicon did. Okay? The work is received by the silicon. So receive, that will make your energy increases, so therefore it's plus. So you have plus 11 kilojoules. Right? Right. So now you have both of them you identify. So both of them have the same unit. And you will just write 3.214 kJ plus 11 kJ. And obviously this will give us 14.214 kJ, which is 14 kJ. So I think that it's getting a little easier in this structure. I think that so right now we just started this silicon as a whole part. Okay? So later on we will become more precise. So if our silicon is like those is something that we can specify, okay? And then we can specify those energy change per part of something. Okay? So right now we kind of is very broad. We see this is our all the energy for all the silicon. Right. So you can see in the last equation what we use is that equation. So that equation is delta E something, okay? Maybe silicon or maybe surrounding equals Q plus W. Q plus W. And so what we said, why we started this chapter? Because chemistry is about matters behavior or matters change. So you have those chemical reactions that usually will produce heat, absorb heat, do work and perform work. So it's very interesting, very important sometimes you calculate what is the heat, what are the work. So one section in this chapter is about calculation those heat. So the heat absorbed or released by the silicon, and as I said before, here we emphasize the silicon. But which part of the universe you call that silicon, which part you call that surrounding, you can change. Okay? So what I said here, equivalently you can use, if you want to change the name, you call that for the surrounding. Alright. So you can, if you want to calculate the heat absorbed or released by the silicon, you can either measure the temperature change for the silicon. If you can measure that easily, or you can measure the temperature change of the surrounding. And what we said before in our lab, we do those powder and those foods. we said we cannot measure that easily the temperature change of the power count. So what we measure is measure the temperature change of those surroundings. Right? So if we call that the power count plus oxygen gas is the only part of our system, everything else is our surrounding. You want to measure precisely all those is also impossible. So what we make our problem simple is just say our surrounding is only that much gram of water. We even forget about those count. So later on you will see why we can neglect, why we can omit the heat absorbed or released by the aluminum can. Right? So once you measure this, and then you find out within some range, within some temperature range, and the change in temperature is directly proportional to the amount of heat that's absorbed or released. So if we still use Q for the heat, and this statement tells you, so Q is directly, if I use this sign, means proportion to the delta T. Right. So here we're assuming this Q is for the system. I probably use the notation so that make that a little more precise. But otherwise, you will have a negative sign for the kind of become not really directly proportional. Right? So that you can always change the proportional. So this is proportional. So this is this word proportional. You can rewrite this Q equals C times delta T. Right? So the C is the so-called heat capacity for some objects. For an object. Your object is somehow equivalent to your system or surrounding. Right? So this come out from our observation. So it's a proportional relation or directly proportional relation. So therefore we replace that directly proportional by a constant. And we call this constant is our heat capacity for our system. Right? So then this heat capacity is one of the capacity we want to study this chapter. Right? It has these two possible units. Okay. Or actually, these two units are exactly the same, even though they look different. Right? And now let's see, you can write that two units in different formats. So this is Joule over Celsius. The other one is Joule over Kelvin. Okay. So as I said, what we studied in Chapter 1. Okay. So this is per 1 Celsius. Per 1 Celsius increases or decreases. And per 1 Kelvin increases or decreases. Okay. Right? Because size of 1 K equals 1 Celsius. So therefore these two units are the same. I just said the size of 1 K equals 1 Celsius. That not means when you measure the temperature, like the temperature today is about like 20 degrees Celsius. Right? So like that. Right. Like today's time let's say 20 degrees Celsius. Okay. Well, then in Kelvin, you get 293 Kelvin, right? So then obviously these two numbers are not the same, right? So let's say terminal temperature increases, okay? So if terminal the temperature, right, is 22 degrees Celsius, right? Now what will be the terminal's temperature in Kelvin? 295, right? So how much temperature change today is with terminals in Celsius? 2 Celsius. How much change is in Kelvins? 2 Kelvins. Okay? So therefore, the size of Kelvin and Celsius are the same. Right? So those are kind of review. Right? So what do you call this C? Okay? So this C is in this equation. So when you have that Q equal to C and times delta T. Now if you want to make it a little precise, you will call all of them the same, referring to the same. Right? So you will say this is Q cysteine equals C, capital C cysteine. So I will use the capital C. Then times delta T of the cysteine. Alright? Okay, so that's similar writing. Now let's see what this guy depends. So this guy call this heat capacity is a very simple name. We call that capital C. Capital C. Okay. It depends on 2 things. Depends on what? What do you have? Depends on how much. Depends on how much it was. How much you have. It depends on these 2 things. So that's good, right? So depend on what you have, depend on how much you have. You can see, for example, let's see, we isolate what we have. We say what we have is water. Okay? And then you will say, because of this proportional relation, if you have 200 grams water compared with 100 grams water, so you have the same something, and you want to increase both of these 2. So if you increase both of these 2 by 1 degree Celsius, and so you have twice that much, according to the proportion, you will require twice of the heat. So another comparison is you have different objects. So how much you have are the same. So you have 100 grams of sand and 100 grams of water. And make it like, let's say you want to even like you see the same amount of heat. And so then you will see your temperature change will be different because this guy depends on what you have. Even though you have the same amount, you have 100 grams of sand and 100 grams of water. So you will see pretty soon this C. Okay? For the water is much larger, is usually larger than most of the other things. Okay? So therefore, if this is larger, and you have the same amount of that, okay, and then you have a smaller this to multiply, get the same. And this will tell you, right? It will tell you if you have that 1,000 joule. Okay? So in this equation, if I write this equation here, so I have 1,000 joule here. Now this C will be different. So C, you can see C water. And then you will have the delta T H2O. So let me write them label like e to the 6. 1,000 joule equals C H2O times delta T H2O. And on the other side, I write 1,000 joule equals C sin times delta T sin. So then I will tell you like this C H2O larger than C sin. Right? So you have those number as written like that. And if you just simply write them like that, you can solve the equation for delta T H2O and for delta T sin, right? Really easy, very easy to solve because you have that equation for delta T H2O, right? And this equation for delta T sin, and both of them has 1,000 joule in it. Because I tell you, you just use 1,000 joule in both of them. So you have 1,000 joule divided by C, capital C, H2O, and then 1,000 joule divided by capital C, sin. And I tell you which C is larger. Which C is larger? You don't know that. The heat capacity of water is larger than sand. Why? Because like in deserts, you know the temperature change very quick, right? In deserts, like like the west part of the country, and the day temperature is getting very hot, but the evening temperature can getting very cool, right? So therefore, in this particular example, you will see that you can calculate precisely for the water, for 100 gram water, with that amount of heat, the temperature change only 2.4 Celsius. Right? So the same amount of heat make the 100 gram of sand change 12 degrees Celsius. So therefore, like that's why, like on Mars, on Moon, right? So if you like want to live on Mars, Mars is pretty much sand, no waters, and so the day temperature become very hot. So because day temperature, the sun shine and the sun will absorb heat, and that will change temperature very quick. And so that's about that. Right. So now we know that a C, that a capital C, okay? That capital C, if I rewrite the capital C, is so-called heat capacity. Depend on two things. Depend on what, and depend on how much. Depend on how much. All right. So now we want to isolate one variable out. So we don't have to worry about how much we have. We just say we only have one something. Right? So we will say 1 gram. That's how much we have. Or we have 1 mole. But most of the time we will say we have 1 gram. Understand? So once we isolate, we only have 1 gram of something, then we will have this guy. We call that specific. If we have 1 more, we will call that molar heat capacity. You don't use that too much. You don't use the molar too much. So most of the time, just isolate, you have 1 gram. All right. So therefore, not per object. So this one, so this guy is per object. And your object maybe 100 gram H2O or 200 gram H2O. Okay? So this is about the heat capacity is about per object, okay? Or per system. How much your system has, that's including everything in your system. If you have a 200 gram water, that means that capital C is for 200 gram water. So if you divide, okay, the total gram of the object out, what you find out is kind of interesting. Okay, you call that specific heat capacity, call that little c and little s. And that is kind of like fingerprints or DNA. It's very similar as density. Okay? It's very unique for those pure substance. So this COS is called intrinsic, which means depending on what material you have. If you have, for example, like copper, and you will have a specific number. If you have water, so you will have a specific number. Then the unit, so let's compare. The unit we said that before, the capital C. We have joule per Celsius or joule per Kelvin. Understand? What do we call this guy? Heat capacity. So heat capacity has these two units. Understand? So this is our symbol. Our symbol for the heat capacity is a capital C. Okay? And remember what we talked about, that depends on two things, depends on what you have, depends on how much you have. So this capital C is about the heat capacity, okay? Depends on what you have, depends on how much you have. So therefore, you don't have those per gram or per mole here at the bottom. Okay? Now this guy is so I will rewrite, just emphasize specific heat capacity and little c. So this is the lower, and the little s. So these are our symbol for the heat capacity, and that's the unit. And those guys write sometimes, if you are first time seeing, you probably don't know what it really is standing for. Okay? So that means you have a joule on top, then you have both of these at the bottom. Okay? Or you can have joule on top and both of this at the bottom. You can use different units for the energy. You can use joule, you can use calorie. Okay? But so commonly you will see per gram, because at the bottom is per, right? So this is per gram, and this is per what? Per Celsius. Right? So let me write that. These two are equal. So these two are equal. All right. So that's, and you can see the difference between this unit. You can tell the difference right away. Right? From the unit, you can see if you have this unit, which means you have a specific heat capacity, little CS. If you have this or this, you have what? Heat capacity. What is the relation? There's a relation between these two. Right? So this capital C equals mass, let me write them out, times C of S in gram. You can also, as I said before, use the molar heat capacity. Okay? So molar heat capacity unit, one possible unit, common unit, will be joule per mole and then per Celsius. Right. So that is about the heat capacities. But once you know the heat capacity, you can calculate what is the Q. So in the previous examples, remember I tell you use this equation to get this number, and I tell you what is the Q, what is W. So now we will learn how to calculate this Q and W if I have some of those informations. Right. So two equations. If you have that C, the Q will equals capital C times delta T. And so if you have the little C of S, you will take this mass and C of S and delta T. So depending on what information you have. So as I said before, right? Because Q and the Q, that means how much heat you release overall. Okay? So therefore you have the capital C equals mass times C of S. To make these two equations are the same, right? These are the same. In both of them you have delta T. So therefore, in order to have both of them the same, the capital C must equals the mass C times C of S. Alright. So let's see those intrinsic properties. You can see for those pure substance, lead 0.128 have very, very small heat capacity. Well, I think that's why the reason in the present time people use lead as a cooking verse, because it's conducting electricity, the conducting heat very good. Yeah, so that's yeah.
So we did, in the experiment, we were able to like not worry about the aluminum because it was had a low heat capacity?
Well, aluminum actually has heat capacity relatively high. Yeah, what I said, I compared aluminum can with water. Okay. So both of them, let's say, increase by 1 degree Celsius. This needs about 4 times more heat than that. So therefore, the heat absorbed or released from the aluminum can is relatively negligible.
Okay.
All right. So read this. I'll be right back. All right. I think, Brad, that's a good question. That's a good comment. So because you have those different heat capacities for different materials, So if you have a lot of material have a very small heat capacity, therefore the heat absorbed or released by those you can negligible. So therefore, we have some very good approximation when we measure the heat absorbed by the surrounding. We only measure that by the water. So as I said, in this section we will learn how to calculate the Q. So therefore, depending on what information you have, if I tell you the specific heat capacity, which is CS, right, and you use this equation, right? So then, if you calculate, and you will see all those number, all the unit come out, and the sign also makes sense, right? The sign also makes sense. So what we saw before, in what kind of process your Q is plus? Absorb heat or release heat? Absorb heat. So now you think about when you absorb heat, whatever happens to the temperature of something you consider increases. So when you have the temperature increases, which means delta T is positive. Right? You can see those mass can never be negative. And C of S in the table we saw, we just define those C of S as a positive number. Right? So you have a positive number, if you absorb heat, the temperature increases a positive number, so therefore you have a positive Q. Right? So then you can also calculate precisely how much it absorbs, right? And by taking the gram, multiply by C of S, and then multiply by the delta T. If you don't know C of S, right, or if you want to do the calculation in another way, you know C of S, you also know the mass, and you take the C of S times the mass, so you together, these two together, you call the capital C. And then you just multiply by the temperature change, right? And that also gives you the heat absorbed or released. Now, by the way, how you calculate delta T? Delta T should equals T what minus T what? Any change. Okay? So this guy means change. Okay? So we will use F for the final, and we'll use I for the initial at the beginning. So that's the very, very important, very basic concept. So anything change, always the final minus the initial. Alright, so let's see this example. I thought we were going like more than I expected. Not that. Suppose you find a copper penny was maintained before 1982. So we change the material we use in the penny. Before 1982, we use like the pure coppers. Right? So then we know what material we have now. We have the pure coppers. Then ask you to calculate how much heat absorbed or released, okay? And which means you want to get the Q. Right? And obviously you cannot use those equations because you don't know what is that, right? So what you think about is use Q equals capital C times delta T, or that Q equals M times C of S times delta T. Yeah, so you make sure you just you want to calculate something, you know, like that's referring to the same, right? So do we know the mass? Let's make a list here. Do we know the mass? M equals what?
3.110
Very good. So that's very, very like good. We know that is 3.1 gram. What unit we use depend on this guy, right? You see in this guy, so we have a C of S. So by the way, with C of S is given in this problem. Okay? Now let me just rewrite this number in a different format. You will see the unit is very clear. So we have 0.3850, and then gram is in the denominator. What else is in the denominator? Very good. So you have a Celsius. These two you can think about they are multiplied. Right, so now what you need to usually use for the mass, for the little n, depending on this guy. If here is more, you want to use more, right? Now here is a gram, so therefore you want to keep it as a gram. So if I give you a kilogram, and obviously you have to convert the kilogram into the gram, then put it into the equation. Right? So similar for the delta T. So we have this temperature unit in the Celsius. If I give you Kelvin, you don't have to do any change. Just subtracting the Kelvin, the initial final Kelvin with the initial Kelvin, you then get the delta T Kelvin, that is same as delta T Celsius. But if I give you Fahrenheit, so make sure you convert those Fahrenheit into Celsius, then do the subtraction. Probably most of the time in this chapter we don't even bother to convert the temperature, but those become like relatively easy. Okay, now delta T equals TF minus TI. Okay, now just read the question and calculate what is our TF? What is our TF?
45.
Yeah, so you have so very good. You already did like the subtraction, right? So then minus what our TI? Negative. So I just do like liberal in details. So then you are right. So obviously this together become 45.0 degrees Celsius. All right. So we make it through. We have those units, right? Right. And just substitute. You have 3.10 gram here, and you have 0.385 joule over gram over Celsius here, okay? And then here you have 45.0 Celsius. This is good. And then you can see the cancellation. See the cancellation. Gram and gram cancel out, right? And Celsius cancel out. Yes, so then the calculation becomes very straightforward. So you take 3.1 and times 0.385, then times 45. Right, 3.1 times 385 times 45. Then right, you have 53.7 joules. Right, so that is one example of doing this in a big chapter. That's all right. Okay, so I think we just start on this chapter. So people study those CIE, read the chapter. Okay, we will do the lab studying water hardness.
So it's like micro corrections and shit. I did read it a few times.
You can use
They need me help, email me or text me or call me.
otherwise sodium, ammonium. So you saw it in the introduction.
So this one is good.
So if you get the grams at 60% yield,
I know it's
right
like
here,
you
so
get
then
the check.
you do this for every 4 grams,
That's
1 gram of
4
one,
grams.
this gram of one.
So that means you get 60% assuming you have the dry wine or
Yeah, I
the
just took the
wine.
water off of it. It's
Yeah.
all
It was 13,
Don't take the water out.
Well, it said it was
All the
dry.
No, that's not that wine. Not that wine. So once you have this, let's see, you have this,
Because they were hauling at the end.
this, you just have like, serenity yields, what is already from the last one? Serenity yields,
Thanks, Jack, I'll see you later.
so serenity yields,
So
what,
it's 80% is this.
okay, so that's your serenity yield, right?
Yeah,
What you do here, just take this 327
okay,
times like 60%,
yeah,
you get an actual yield.
yeah, I did that.
Yeah, so then you don't have to change letting drive. So then what it wet means, once you take this 327 times upon the 6,
Mhm.
you get the super drive for this 60%. Then what you do, they tell you for every 4 gram of aluminum, because those dry wine, you will have 1 gram of water.
Okay,
So once you have this upon the 6 times 327, then you will divide by 4.
okay,
So that will convert into how many 4 gram of those material you have.
okay.
So then for every 4 gram you are adding 1 gram of water.
So you just add 18.
Yeah, so just, you pretty
What
much,
is the-
you see that's-
is more mass of water? 18?
no. So what you see, you will have the 327, right?
Mhm.
That's the theoretical yield.
Right,
And then you will see times upon 6, that is where you have 60%.
yeah,
And this is how much dry aluminum you can get.
oh, okay,
Now for every 4 gram of this dry aluminum, so you will take, you will divide by 4. It's kind of those conversion ratios, what we studied, like you have this 196, okay? So those are dry aluminum.
okay.
And then there's quite a tell you for every 4 dry, you have 1 gram of water
So it's just a
in
ratio.
it, so that's just a ratio.
Okay.
So then total you will get, you still have this dry.
Okay,
The dry, the 196 plus this part is how much water we have in it.
okay, so you're at it, yeah, okay. That's like that one, number 3 in that one chapter.
Roger?
Yeah,
Just a minute, let me give you,
take your time, so.
Well, we didn't put down.
for you, okay, so here is your, let me see the, downwards one, take a look.
Yeah, okay.
So that you already find the scan out for you. Okay, what's the question?
Cool, for the quiz on chapter 5, I was able to do it, but there were 2 questions on there that I had to guess on. And I was wondering if you could help me work through them really quick.
Okay.
One was number 13 here.
Mm-hmm.
I think it's about fusion.
Mm-hmm.
I was wondering what equation I would use to do this one here.
Okay, so use that diffusion ratio, so you know that you have that. Okay, so you have that, so you have that rate, line R down, and rate, the other one is the unknown. That equals square root over the molar mass of the unknown, and then the molar mass of R.
Right.
Okay, so you have those rate ratio. So you have
Right,
that.
so I've got the rate of xenon, right, which is 75 seconds for I'm sorry.
Yeah, you can see those seconds, see the rate, or this opposite as a second, as a time will take.
Okay. So wait, should I replace, should it be xenon, not argon, right?
Well, let's see, you have, what is the number for xenon? Not xenon, not argon, we have one other argon, xenon, right?
Yeah.
So it's xenon. So that you know the time it take is reversely as the rate.
It's 75 seconds,
So
so.
let's say rate or equals how much we have, and then divided by how much time we take.
Oh, okay.
So therefore, this relation is about this. So obviously, this written time is inversely proportional. So therefore, for time, just use the reverse. Right. So this, let's see, this, I know this, we keep this side still dead, and this is still our xenon. Okay. So therefore, the time I will use on top is for the unknown, on the bottom is for xenon. You can see here. If I rewrite this equation, so T1 equals V divided by the rate.
Okay.
Now, if you still want to use that equation, let's see this equation. You see this rate xenon divided by the rate unknown. Substitute those equations.
Okay. The only thing I don't get is that's the volume, right?
That's one.
Right. The only thing is it doesn't give you a volume or a
The
mass.
one work out. So it doesn't work.
Okay.
When you see that, see, we have this equation, right? So I just see like the same volume. So I see this volume, okay? And then divided by T xenon. That's on the top.
Yeah. So
Okay?
you're just substituting that equation in.
Yeah.
Okay, I
So
got it.
then you will see this will be V because we are the same. You divide by the T unknown.
Okay.
Right. So then you keep it right. So this will be V divided by T xenon. Divide means multiply by the inverse reciprocal. So this becomes T unknown. See what I write here? So this is V over T xenon, so I just write here.
So this is assuming.
That's in the numerator.
Okay, so you just flipped it.
Yeah, freeway.
Yeah, you just turned the bottom.
Okay, so this is assume that the volumes are the same.
Right.
Both-
So this means, yeah, this means divide, so therefore the volume is the same, and we're assuming that.
Oh, okay, so it's just the time of the unknown then over the time
Yeah,
of xenon.
In the initial equation, you can replace those kind of relations. But if I give you time, so you just, for this problem, so you gotta write this as this format, and then the time of the reverse, so that means the time for the unknown on top.
Okay. Alright then, so hold on. So if you did that, all you'd have then is T unknown over
Yeah.
T xenon.
Exactly.
So the unknown I gave you 75 over 34.5 is equal to, and molar mass of,
The unknown on top,
yeah, that's what we need,
and then more mass of the xenon you can find out.
which is 131.
Yeah, probably, yeah. So then you just, very easy, you just square them both,
Oh, so you square both sides.
so that they'll come out.
Okay, and then whatever you get for your molar mass, you just look on the periodic table,
Yeah,
and
yeah.
it's should be nitrogen. Okay, that makes sense. Thank you.
Okay.
There was one more I had a problem with.
Okay,
I'm sorry.
this way. Right, sometime.
It was 14. It's considered a generic reaction.
Okay. Okay, so you have this generic equation, 2A and 1B produce 2C, right? If a flask initially contains this much ATM of A and 1 ATM of B, what will be the pressure in the flask if 1.5, what will the pressure in the flask if complete? So they have, assuming they have a constant volume and constant temperature. Alright, you have to find out, this is 2 and 1 ratio, right? You probably want to find out, so we have that equation, we assuming an ideal gas equation. Let's see those pressures, right? So the pressure A or equals that N of A times RT divided by weight.
Alright,
So it's pretty much the pressure pretty much proportional to the number of mole.
right, okay.
And then pressure of B will equals N of B RT divided by weight. If those are constant temperature, constant volume, so you have two of those V plus one of A. Am I right?
No, it's 2A, 1B.
2A. That makes sense. And then for the 2C. Right, now, right now this is equals 1.5 ATM. This is 1.0 ATM.
Okay.
Right? Let's see how much, what are the limiting reactants? 1.0 ATM of this is proportional to some moles. See what I said? 1.0 of this, according to the mole ratio, so this is B, right? And how much more of A, how much more of A do you need? How much ATM of A do you need?
2.
2.
For everyone.
For everyone. So now you have only 1.5. Now vice versa, if 1.5, so 1.5 of A, and how much B can you use?
1.
2 you use 1.
Oh.
If 1.5, you can, so those ATM ratios become mole ratios. 1.5 ATMA, and from this coefficient, those coefficients can be used as the ATM ratios because this can divide out to become what we did for the last problem. So RT will divide out, it becomes same as mole ratios.
Yeah, so on the bottom you have ATMA.
Right. So on the bottom we have 2 ATMA, and then 1 ATMB.
Okay.
So therefore, for 1.5 ATM of A, according to the ratio, the ATM A, ATM B come out, so that require 0.75 ATM. And this is because that's needed. We need that much of B. Right? Now how much B is available?
Sorry?
How much B is available?
The
One pressure is available. This is needed, and this is available. We did not talk about those ways to find out the limiting reactants.
That's why I was confused.
Right? Yeah. So what is the limiting reactant?
It'd be B, right? Because that's, no wait, it'd be,
You see, you need this much. You only need 0.5, and you have that available. So you have more than what we need. So B is the excess.
okay.
So A is the limiting reactant. So A will be always used up. Right? So A will used up, and then how much B will ever over? Initially you have 1.5, so that will be our initial. This much of A. Final with the finish 0 ATM of A. Which means you use all the 1.5. If you use all the 1.5 ATM of A, how much B do you use? So 1.5 use more ratio, we get 0.75 ATM of B. But how much is available? So then we will have those left over. So we have 1.0 minus 0.75 equals 0.25.
So that's what's excess of B?
This is how much B pressure still left over. What's the question? The question asking the total pressure, right? After the chemical reaction finished.
What would be the pressure in the flask if the reaction?
In the flask, so you will see like how much C pressure will convert. The more ratio again. So how much? Let's see how much A we use. A is a limiting reactant, so therefore A is all gone. Right? And A all gone, because initially you have 1.5, final becomes 0. Right?
Yeah, so you do 1.5
There you go,
ATM
1.5
A.
ATM A used.
Yeah, you times that by 2 on the bottom.
Yeah, two ATM.
Two
Two ATM A.
And then 2 ATM C.
Yeah, 2 ATM C. And then you just get 1.5 ATM for C.
Okay.
So after reaction finish, you don't have any pressure from A anymore. But you still have this much pressure from B.
Left over.
That will work. Then we also generate some pressure from C.
So you just add the two together?
Yeah.
Get your
Okay, the total pressure.
Alright.
It's kind of interesting question, yeah.
Yeah.
But we don't study a lot of those, so therefore, I find those just kind of like those actual you can do some of those practice.
Cool. So that would not be on the test.
Probably.
Oh, sorry, I found that. Alright, thank you. Have a good one.
Thanks.
Okay,